Okay, in this chapter, we're going to talk about friction. Now, friction is basically when two materials come together and see how much grip there is. Okay, now let me look through here. If you look at paper through a microscope, you'll see that it has a lot of strands in it, and it's actually kind of rough. And the reason why a pencil writes so well on paper is because it's rough. So as the pencil tip goes across, it's rubbing off there. Plastic, if you've ever cut yourself on plastic, it's really bad. Or if you've ever played on AstroTurf is very, very similar to plastic. It's like little molecular mountains, and if you slide across it, it just tears you apart like concrete. Glass is pretty smooth. It only has a couple little ridges. It's not too bad. But now what's really cool is if you look at the bottom of a gecko's foot, if you look at that and the shape of this foot, all right, the pads of it allow for maximum grip so that it can actually walk right up a tree, walk up a glass window. It has an amazing amount of grip. Now, think back to like the 1990s. Remember the sneaker that was out there that looked like this? It was called, I think it was by Reebok. It was called a Ziggs. All right. Everyone had to have them when they were in school back then because, oh, they got maximum amount of grip. You can go super, super fast. You can jump even higher, blah, blah, blah. All right. It was kind of like what everyone wanted. All right. Um, the Ziggs had a very similar pattern as the gecko's foot. All right. So it kind of makes sense. All right. Now, this is a picture of, it's kind of a computer generated picture of why things slide with lubrication. All right. Did you ever hear of WD 40 or silicone spray, stuff like that? What it basically does is that a surface has a lot of ridges. If you spray something across and get rid of those ridges so it's level, it's easier to slide something. Okay. And that's basically what's happening is this looks like almost like an eggshell container. And if you fill in the holes of the eggshell container with like a silicon lubricant or something like that, it'll actually, things will glide across it. If you're, and people who have experienced this is driving down the road. If you hydroplane, you hit a big pocket of water over a hole or something like that, all right, you lose control. Or ice. What happens to ice? Ice bevels right up over the top of that, all that grip. Okay, and you slide. All right. So that's an example of that. All right, friction, a force which opposes motion. And there are two types of friction. The first one's called static friction, and that is the force exerted on a stationary object to get the object to move. Okay. So if you're sitting in your chair and I come up behind you and push, 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 and then you start to move. If I had like a bathroom scale and I had it on your back as I was doing this, I could find out how much force I need to push to get you to move. Okay, and that amount of force would be the force of static friction. All right. In lab, you're going to hook a spring scale onto a block and you're going to pull, and it's going to just get moving. All right. When it first starts to get moving, you read the number, and that's the static friction. If you pull at a constant speed, that number will be less than the number you use to get it to move, and we call that kinetic friction, which we'll see in a second. All right. So if you hooked a spring scale onto a block and started to pull slowly, you would see the force meter would keep increasing until the object begins to move. That is the maximum static frictional force. We can calculate the coefficient of static friction between two surfaces by doing just that and using the following formula. The force of static friction is equal to the coefficient of static friction times the normal force. Okay. Now I put this in here too. All right. A little greater than less than sign here, right? Because sometimes if there's like lubrications and stuff involved, it comes out to be a little bit different. All right. But most of the time when you see this formula, it's just an equal sign. Okay. And in fact, in your book, I think it is an equal sign. The normal force, F of n, is the normal force. And remember what normal force is: mass times gravity. okay? If it's on an incline, it'd be mass gravity times the cosine of the angle, okay? All right. How much force would be necessary to get a 240 kilogram stationary wooden crate to move on a wooden floor? Now, I'm going to say there's all sorts of woods. There's pine, there's oak, there's cherry, there's finished wood, there's unfinished wood, there's decking. There's so many different types of woods. They all have different coefficients of friction. So I'm just going to say wood on wood's 0.42 for this occurrence. All right. So the force of friction is equal to 0.42 times 240 kilograms times 9.81. And your force of friction would be 988.85 newtons. So if you had a 240 kilogram crate, it would take you 988.85 newtons to get it to move. Okay? That's what that basically means. No, the surface area of friction does not matter. It only matters between the two materials present. So if I had something sliding across the ground like this, or if I had it like this, theoretically, it should be the same number because it's the same material, but surface area should not matter, okay? What usually happens is people make an analogy with something that's larger having more friction, like a tire, okay? Let's say if you have a fat tire versus a skinny tire, which one has more friction? Well, this is the thing. A fat tire weighs more, which is F of N, okay? So you get more friction, but the coefficient is still the same, okay? Versus a skinny tire, all right? So these two, if you pulled them like this and this, they would come out to be the same, all right? But misconceptions are like that. You have to take everything into consideration. All right, kinetic friction is the force exerted on an object to keep the object moving with constant speed. Because remember, what's constant speed? Constant speed means there's no acceleration. It's going the same speed, okay? So force of friction kinetic, that's the little k, equals a coefficient of kinetic friction times the normal force, all right, which is the weight. How much force would be necessary to keep the 240 kilogram wooden crate moving across the wooden floor at a constant speed? Well, the kinetic coefficient of friction for wood on wood, instead of 0.42 being static, is 0.3. It's less. Remember, the closer to 0 you get, the slipperier the object is. The closer to 1, the stickier the object is. Okay? So you could put in 0.3. Now you notice, what are the units for coefficient of friction? There are none, because coefficient of friction is newtons over newtons and they cancel out. That's why there's no unit here. Okay, this is like one of the only things you're going to see all year long that doesn't have any units. It's coefficient of friction. So it's 0.3 times 240 times 9.81. You get 706.32 newtons. So you're talking almost 300 newtons less to get this object moving at constant speed, which makes sense because when you start pushing something, it's harder to get it to move, but once it's moving, it moves easier. Okay, and that's exactly what's happening. All right. Did you ever pull a kid on a sled? All right, when you first start pulling, it's hard, but once they start moving, it's pretty easy. All right, there's a huge difference, and that has to do with the different coefficients. All right. Here's an example here. John is dragging a 16 kilogram box across the floor that has a coefficient of 0.4 at constant speed. How much force is he using to pull it? Well, 16 kilograms is what? It's the mass. It's not the weight. All right, it's not the normal force. So it's 16 kilograms times gravity. That's what you're going to want to use. All right. And it says moving at constant speed means the force applied is equal to the force of friction. Since it's moving, it's kinetic. So it's 0.4 times 16 times 9.81, and your answer comes out to be 62.78 newtons. All right. Fluid friction. Now, this is an interesting topic because especially like if you work on cars, if you have a lift, a grease gun, a tube of toothpaste, this is fluid friction at work. Okay, when a solid object is in contact with a fluid, such as a liquid or gas, and a force is applied to either the object or to the fluid, there's a frictional force that resists the motion. Examples where fluid friction occur are water flowing through a hose, an airplane flying through the atmosphere, and oil lubricating moving parts. Now, it's interesting that I put a plane flying through the atmosphere. All right. Air is a fluid. And if you did not have air as a fluid, you could never fly, because when a plane wing goes through the air, the fluid, the air, goes over the top and the bottom. The way the wing is contoured, the air going over the top of the wing is covering a larger distance in the same amount of time than is underneath the wing. So technically it's going faster. Because air moves faster over the top of a wing, it has a lower pressure, and this is a higher pressure down here. So, and pressure always goes from high pressure to low pressure. So that actually causes lift. And that's how a plane flies. All right. It's pretty cool. And if you've ever looked at some of those scientific things with aerodynamics and stuff, they have a smoke chamber and they can see the smoke going over the wings and stuff like that. Or if you've actually driven a car and you're trying to like pass a semi, you could feel all that wind blowing on you. All right. Now, back here, if the viscosity or thickness of a fluid is great, there may be no movement due to static friction. One example is trying to move heavy grease through a hose. All right. You need to apply a great pressure to finally break the static friction and start the grease moving. If you've ever used a grease gun, where you squeeze it like this, you put it on there to lubricate the joints on your car. When you first do it, it's like real hard, and then all of a sudden it gets real easy to do because it's pushed through. All right. Or think about toothpaste. Maybe that it had maybe it didn't have the cap on. All right, it gets kind of funky on the end. All right, when you squeeze, it's hard, and then once it breaks through, then it comes out pretty easy. Or even a caulking gun, same type of thing. All right, when you first do it, it's getting through that nozzle. Once it gets out the nozzle, then it goes through a lot easier. All right, and that's all with viscosity. All right, so once a fluid moves through a hose or an object is moving along a fluid, the resistance is now considered kinetic friction, and we know kinetic friction is always less than static friction. That's why it's easier. The grease will still move much slower than a fluid with low viscosity like water. So the thicker the object, the slower it's going to go. All right. Causes of fluid friction are turbulence effects from the surface roughness and deformities. From the surface roughness and deformities, molecular attraction or adhesion between the materials, and deformation resistance of the fluid. This deformation resistance is called viscosity. Where have you ever heard the term viscosity? For me, if I've ever watched NASCAR or Indy, there's always commercials for motor oil, and they talk about viscosity and they talk about thermal breakdown. All right. I think if you know anything about going to the store and getting your oil changed, oil comes in many different types. You could have 0W30, you could have 5W40 or 10W40, right? There's literally like different thicknesses, okay? The W does not stand for weight. It actually stands for winter. And the history behind that is like if you had a car like back in the 50s and 60s, you might put 10W40 in the car during the summer because it's a thicker oil. But in the winter, you might put 10W30 in because it's a little thinner, and in the winter, it's harder to get your engine started. All right? That's kind of a little history thing there. I never knew that for years, but it was kind of cool. So that's this chapter. All right.